Hello, everyone. Welcome to the Cambridge University Astronomical Society's weekly talk. I'm Xavier, the chairperson of the society. Tonight, we have Professor Richard Horne with us to give a talk titled Severe Space Weather. Before we begin, allow me to share a little more about our speaker. Professor Richard Horne, FRS, is head of space weather at British Antarctic Survey and an honorary professor at the University of Sheffield. He has published over 200 research papers on wave-particle interactions, wave propagation, and space weather. He led the EU Spacecast project to develop a space weather forecasting system for satellites, and the EU Space Storm project, which showed that the risk to satellites from space weather is much higher than previously thought. Richard's work led to the revised hazard assessment for the UK National Risk Register of Civil Emergencies in 2017. He is co-chair of the Space Environment Impacts Expert Group, which provides advice on space weather to the UK Cabinet Council. In 2020, Richard was awarded the International Christian Birkeland Medal for Space Weather and Space Climate, the URSI Appleton Prize for research leading to the practical space weather forecasting, and a Doctor of Science from the University of Cambridge for distinguished research. Richard was elected Fellow of the Royal Society in 2021. He is also a Fellow of the American Geophysical Union, the International Union of Radio Science, the Royal Astronomical Society, and St. Edmund's College, Cambridge. Now, without further ado, Professor Horne, please.
Okay, thank you. Thank you very much, Xishen. Thank you very much. That's very kind of you. And it's lovely to be here and to try and give a talk tonight on severe space weather. So, okay, I'm going to give a sort of fairly broad overview of all the aspects of space weather. And then towards the end, I'm going to give perhaps a little bit more detail about some of the things that we're doing at the British Antarctic Survey, my team, to actually try and forecast the periods of high risk for satellites. So actually on this plot, on this figure, let's make sure, yeah, okay. So this kind of gives you the overview, the big picture, if you like, to start with. The sun over here and material coming off of the sun, which is in the form of high energy charged particles, mostly protons and electrons, flowing towards the Earth. And then over here, you see the Earth, and the lines represent the Earth's magnetic field. Close to the Earth, you can see it looks like a dipole. But as you go further away from the Earth, you can see the Earth's magnetic field is distorted. And it's distorted by the flow of material which comes across the Earth's field and then flows around it. Most of it flows around it and distorts the outer layers of the Earth's field. So we'll talk about that a little bit more. In here, color-coded in red, I don't know if people online can see this. Perhaps they can't see it online. Maybe I should show this, do this. Are the Earth's radiation belts. These represent regions of very high energy charged particles, electrons mostly, but electrons and protons, which are trapped in the external magnetic field of the Earth and which circulate all the way around the Earth, and which we'll also talk about a little bit later. They present a hazard for satellites on orbit. And this whole system, well, space weather starts with the sun, but actually all the impacts are felt at the Earth. And so, okay, so we're going to spend most of our time talking about what happens around the Earth. Okay, so we're going to talk about systems affected by the space weather. Talk about coronal mass ejections, their effects, and how they affect the power grids, satellites, GPS communications. So a little bit about radiation storms and their effects, particularly on aviation and satellites. I'll throw in a few numbers about economic uncertainty, how difficult it is to calculate and quantify what the impacts can be, and then we'll talk a little bit about some of the challenges. So this again is another sort of big overview. I just want to give you a picture of all the sort of systems that can be affected. So if you start up here on the top, you see satellites, high energy charged particles in the radiation belts I just described, trapped inside the Earth's magnetic field, can damage the electronic components on satellites. Radiation storms at the sun also emit very high energy protons, which can reach the Earth, penetrate the Earth's field, and cause damage to satellites, and disrupt the services and the signals that they provide. Coming down, you can see and if you remember, if your current has a magnetic field associated with it as it flows, and if it's highly variable, then the magnetic field is going to change, dB by dt, as I've written down there. And if you remember from your physics, and remember from Maxwell's equations, curl E minus dB by dt, it sets up and induces a electric field. So here we go. And that's what actually upsets the power grid. So here we go, up the top here is the aurora. And think about the electrical currents which flow through the aurora. They're not steady, they're changing all the time, so you have a change in the magnetic field associated with them. That magnetic field induces an electric field down here on the Earth's crust. Now the Earth's crust is quite resistive as it flows, the current flows. But of course, if you've got a power grid, transmission lines going up and down the country, what happens is that some of the current can flow up through the transformers into the power grid and along the transmission lines, and then back down again. And it is that current which actually upsets the transmission line, it upsets the transformers, because the transmission line and the power grid is operating 50 hertz. What you're effectively doing here is you put a current system, you put the electric field on the current system through that, it goes up through the neutral line and is effectively shifting. It's like a DC shift. You've got a 50 hertz going on, but you shifted it, you shifted the baseline. And that means the transformer starts operating outside its design spec, and it can lead to real problems, heating of the transformer, and actually in a famous case in Quebec in 1989 led to burnout of the transformers. So this is what I'm saying. Okay, so the electric field sets up geomagnetically induced current, GIC. Current flows out of the Earth through the transmission lines back to Earth via the neutral line and transformers. And so it can not just do that in the transmission lines, but also along railway lines and oil and gas pipelines, and it upset the protection systems in the oil and gas pipelines. But it's the power grid that's the most important. So just a few events then. 1859 is the Carrington event. It's the largest magnetic storm we know of at the moment, where we have some measurements of it. It disrupted in those days the telegraphy system and caused fires in telegraph offices, partly because they disconnected the system, and the system still worked because he ended up with electric field in the system, and they had flammable paper in the telegraphy office, and some of them caught fire. Caused fires. Easter Sunday, 1940, the first power grid effects, which you noticed in this country. In 1989, there was a blackout in Quebec. 9 hours, 6 million people were affected by that blackout. And here's the picture of the transformer. 90 seconds, that whole thing collapsed. And that's what happened to the transformer. It was burnt out. It's a huge piece of electrical equipment. 2003 Halloween storm, blackout in Malmö, Sweden, damage to transformers also in South Africa, because this happens in both poles. Okay, so it's important. And this, when President Obama got to hear about this stuff a few years ago, he got really concerned because you don't want blackout in the United States. And he started asking, what are we doing to protect this system? And so of course, all the civil servants got together and started thinking, what is this thing called space weather? What do we do? And it raised the priority of it. There was an agreement between the USA and the UK to actually work together on space weather to help protect these systems. And it's not just the power grid. It's the most important is the power grid because it's power. That's really important, but it's wider than that. Okay, so this is the work that Alan Thompson does at British Geological Survey up in Edinburgh. And here they're actually trying to look at what the worst case might be. And what you see here in blue, those sort of circles are different points on the national grid where they're trying to measure and get an idea of what the currents are. And what we're trying to do is assess what the reasonable worst case will be. So, and they originally started doing this in the terms of dB by dt, the rate of change in magnetic field. And the estimate was around about between 1,000 and 6,000 nanotesla per minute over 1 to 2 minute timescale. With that, you expect a voltage instability and regional outages if we got that high. And then there's an influential report done by Paul Cannon. I contributed to that back in 2013 for the Royal Academy of Engineering, showing or suggesting that the realistic worst case was around about damage to 6 grid transformers in England and Wales, and around about 6 in Scotland because of the higher latitude, closer to the Ural region where all these currents take place, so really become intense. So that's some of the work, and that's ongoing. It's always being updated. And there's work now to actually try and reassess this in terms of not just dB by dt, but actually measurements on the grid more carefully and develop much better models for it. I'll move on. Let's talk about effects on satellites and the Earth's radiation belts. So what you see here, play this, yeah. What you see here is the Earth and the Earth's magnetic field, and trapped inside the Earth's magnetic field are the charged particles of the Earth's radiation belts. So these were first discovered back in 1958 by the first US satellite, Explorer 1. And they went through here, and the detector, they're expecting to measure cosmic rays, and they're expecting the flux to go up. And what happened is their detector started increasing the count rate, and then it went to 0. And it took them a little while to find out that what was actually happening is that the detector was being overwhelmed. It just couldn't cope. And they were not cosmic rays. These were charged particles trapped inside the Earth's magnetic field. So the charged particle, you remember, is a spiral around the magnetic field, goes along the field. And as it goes to the northern hemisphere, of course, the field strength increases. You have a gradient in the field. And that acts as to put a force on the particle and pushes the particle back. So the particle will then go along to the opposite hemisphere. And of course, you've got a gradient in the opposite sense in the opposite hemisphere. So that's a force on the particle. And the particle ends up bouncing to and fro. It's trapped. Most of them are trapped. It's not perfect. Most of them are trapped. And then because you have a gradient in the Earth's magnetic field as you go out, the gyro radius of the particle as you go around. As you come in closer to the Earth, the gyro radius is slightly smaller. As you go out, the gyro radius is slightly larger. And that results in a net drift of the particle all the way around the Earth. So these particles will drift all the way around the Earth. And for one MeV particle, it's around about 15 minutes, 10, 15 minutes it takes to go around. So the time scale to go northern hemisphere to the southern hemisphere, maybe a second or two. Time scale for spiral around the field, maybe milliseconds. And the time scale to go all the way around the Earth is about 10, 15 minutes. I'll give you an idea. So the science question here is, these are very high energy particles, electrons, eV energies, millions of electron volts. How do you accelerate particles up to millions of electron volts? The source is either down here in the ionosphere, where the energy is less than 1 electron volt, or it comes in from outer space, but measurements in space show that typically the energy is sort of 10, 100 electron volts. What has been established is this acceleration happens inside the Earth's magnetic field. It has to happen inside the field. And that acceleration, there are two leading theories how you actually do that. One of them I'll talk about perhaps a little bit more detail later. But the idea is that you actually have various types of plasma waves which exist and are excited in this region, caused by charged particle populations, low energy charged particle populations. Excite plasma waves, and then they accelerate a fraction of the electron population to very high energies, which then remain trapped inside here. What you're looking at is really a gigantic particle accelerator. That's what the Earth's magnetic field is doing. I'll come back and I'll show you a little bit more, talk about the physics a little bit more. That is real data. The field is not as a model. But okay, I didn't put the color scale on, but that's real data. That's giving you an idea of the variability of the particle flux. These particles and those radiation belts can change by something like 5 orders of magnitude, and the time scale as short as 90 seconds. Very difficult to forecast. Okay, why is it important? Because damage to satellites. So a number of different ways. I've written down 4 main ways that satellites are damaged. So, okay, single event upsets. A cosmic ray, high energy charged particle, can penetrate the Earth's field quite easily, go through an electronic component, and it can flip a bit from a 1 to a 0, 0 to 1. It deposits charge in the electronic component, and it can corrupt it, and it can happen also down on the ground, actually. But it's fairly easy to correct. Designers now have sort of correction software to correct for that, and they and duplicate circuits. That's okay as long as the flux is fairly low and it doesn't go overwhelmed. So that's one way. Radiation storms, where you have energetic protons from the sun, can also disrupt them. Surface charging is another thing, which is certainly very important during the 80s and still remains important, although we've got large mitigation measures now. You put a spacecraft in the plasma, you've got electrons and ions all the way around it, and they form a sheath around the spacecraft. And that's fine. But when the spacecraft goes into eclipse, and that's the most important or high risk period, you have, okay, in the sunlight, you have photoelectron emission, Einstein's photoelectron emission. But you go into an eclipse, you haven't got the sun on the spacecraft. So you end up with the spacecraft starts to charge up in a negative. And your background population of charged particles is there, and they're bathing this spacecraft in charged particles. And sometimes we can have injections of particles which come in from the tail, the motion of changes in the magnetic field, and they bathe the whole spacecraft and charge it up. So satellite charging up to something like 10 kilovolts has been measured in the past. But of course, every piece of component in the spacecraft may have a different work function. And so different materials can charge up to different levels. And if you get a different charge between one component and another, you can get a spark, if you like, a breakdown between them, and you can break down some of the material and cause permanent damage. Deep dielectric charging, the one over here, is really important. So these particles, this is the radiation belt particles, MEV electrons, I was just saying. These MEV electrons can penetrate the skin of the spacecraft and then go through, they can penetrate sort of 3 or 4 millimeters of aluminium. They go right the way through, and then they get buried in the dielectric, the insulating material inside the spacecraft. So it may be a computer, part of a computer chip or wherever. Of course, it's an insulating material, so the charge can just build up and up and up. And if that flux of particles remains high for a long enough time, the charge can build up and then just breaks down the material. And we've had several examples of spacecraft where if that component is controlling something that's really important, like the spacecraft control computer or the orientation of the spacecraft, you can lose the spacecraft. And we have examples of that. It's been associated with loss of spacecraft. That's it, gone. $250 million on a communication satellite just gone. There is something like over 500 spacecraft at geostationary orbit alone right now. I'll show you some of the stats later. So that is important, and it's very difficult to design against it. You can put shielding around the spacecraft, shielding around the electronic components, which is what they do, but that can increase the weight of the spacecraft and can be quite expensive. Solar ray degradation is another thing. We have high energy particles, mostly the heavy ions, can impact the solar arrays, and they call displacement damage. So you might have a nice sort of crystal structure in your solar rays collecting sunlight and turning to current. But you basically knock out some of the atoms in the crystal structure, and that just degrades your ability to generate power. And so that's one of the things science designers have to take into account. So the radiation belts, proton radiation belt, is actually a concern for that. So you've got to be really careful and design for it. You've got to make sure you've got enough spare capacity. Okay, that's it. So here's an example then. This was an event known as the Halloween storm back in 2003. So Earth's surface, let me just orientate you. The Earth's surface is at 1 down here. This is measured in Earth radii. Geostationary orbit is about 6.6 Earth radii away. So that's, I put this red line going across. And this is time running here. So October, November, December. So you can see it's about 3 months or so. And what we're plotting here is the high energy electron flux, greater than 2 MeV electrons. And you can see this is the electron radiation belt. Mostly, peak of it is around here, around 4 Earth radii. But you can see it's quite variable. It goes and then comes back again. And then we had this big storm, big magnetic storm, which is what I was trying to show at the beginning of that video, where the Earth's magnetic field was disrupted and ripped apart. And what happened in this storm, we had a big increase here. These are solar energetic particles coming in, which didn't last very long. Then we had a depletion here in the radiation belts. And then the radiation belts were formed much closer to the Earth. They were formed in this region here. This is the outer radiation belt. This is the inner radiation belt down here. And between them is a gap. It's called the slot region, which is mostly devoid of particles. And what happened here is the radiation belt was reformed exactly in this region. So the science questions is, how do you actually account for this happening so quickly? The depletions here and the increase down here, and then you see this decay, and then lo and behold, it came back with a vengeance back out here, and highly variable. During this period, one satellite was a total loss, so it's a scientific one, cost $640 million, Japanese. 10 satellites lost service for more than 1 day, 47 reported anomalies, that means malfunctions. That's 10% of the entire fleet which was operating at the time. What would happen today if that happened again, or something worse than that? That's not the worst storm we've ever seen. And that's what people are concerned about just now. Let's try and put it in context. Okay, this is the sunspot number. It's not filtered, so you've got all the variability. Back in 2000, you see the solar cycle, the sunspot number, not okay, a bit less actually over here, 2015 or so, and then just start of the new one. If you look at the blue line, this is the number of satellites in geostationary orbit. It's going up fairly steadily. If you look at the red, these are the satellites in low Earth orbit, Starlink, OneWeb, or those ones, and the constellations. And you see it just starts to go off scale. I did this and I stopped this, I think it was about 2019 or whatever it is. 2000, there's thousands of these things going on. They're all going into low Earth orbit. It's to do internet in the sky. Give you low altitude, they're up about 800, and OneWeb is up around 1100 kilometers altitude, 1200 kilometers altitude. Most satellites in low Earth orbit are either around 500-600 or around 800 kilometers. So that you don't have so much signal delay. So there's thousands of these things being launched. And the UK is going to be in Scotland. We're going to start launching them from Scotland come next year. Virgin is going to start launching, and OneWeb too. So can you imagine what would happen? The question is, how vulnerable are some of these satellites? They've never been through a major set of storms. Look, solar cycle here is being weak. Not had much in the way of storms, nothing like we had over here. So let's hope that they've designed them correctly. withstand what can happen. Here's an example. This again is a radiation belt. We're showing high energy charged particles, MEV electrons. Again, so this is geostationary orbit. This is a period in, remember, yeah, 91, if I remember right, yeah, 91, from here. This is where the radiation belt normally sits, so you can see the variability. And power, we had a different kind of event here. We had a rapid compression of the Earth's magnetic field. We had a coronal mass ejection came along and just compressed the field, the boundary of the Earth's magnetic field, just compressed it right the way in. And associated with that, a new radiation belt was formed in 90 seconds. Down here, usually in a region where it's pretty devoid of particles, in the slot region, and then took months to decay. There's one satellite operator called O3b that launched their satellites and they operate at 8,000 kilometers altitude here, and that black line goes. And they do that because they understood that this region is virtually devoid of particles. It would be safe. So they've never encountered something like this. It'd be interesting to see what would happen if, when they do. Okay, how do you inject particles and create new radiation belt down there so quickly? That's a scientific question, which we work on. There's some ideas around that. Okay, this to give you an idea, there's new modern technology which is coming in too. So the new way of launching spacecraft is to use electric thrusters, electric propulsion. And the idea behind that is, okay, so you reduce the weight, you don't have chemical propellant, you're just using an iron thruster. And that means the amount of thrust is quite weak, so it takes you a long time. But that's okay because you save money on the launch cost. So the idea here, there's 3 different scenarios here in the launch. So the first is that you can do it on elliptic orbit in red. I'm just going to remind myself, yeah, start off in red, in elliptic orbit, and eventually switch the thrusters on at the appropriate times, and eventually increase the orbit out, and you reach geostationary orbit. This was first done in 2015 with Boeing satellites, the first time, all electric propulsion for commercial satellites. Another scenario is you do a highly elliptic orbit out here, and then you switch the thrusters on, and you bring apogee down, and you raise perigee out, and you make it circular. And here's a sort of mix between the two. So three trajectories, 3 types. This is being done by commercial operators. This is SES on 2 of those at least. And then we did a calculation. I think, well, I wonder what would happen if you launched the spacecraft during this period. How much radiation damage would you get? How much would it degrade the power supplies compared to if you launched it here? So myself and a student, we sat down and the student did all the calculations, of course. And we did the 3 different scenarios, and we took a typical solar cell. And we said, if you launched it here during the fairly quiet period, depending on what you do, you get something like, what, 4% degradation, loss of power. That's before you get onto station. If you do it over here, you got something like 8% loss of power. That's before you start operating. That's really significant. Depends upon the thickness of the cover glass, of course, and how much protection you've taken. And then from that, we worked out what the best scenario would be to minimize the radiation damage. So it's kind of an interesting problem. And just to highlight, okay, this is, I wanted to highlight here, most satellites, as I said, operate around 800 kilometers in low Earth orbit. And this is South Atlantic. There's a weakness in the Earth's magnetic field. So those particles which go bouncing to and fro, they can actually go penetrate closer to the Earth than the South Atlantic because the magnetic field is weaker there. So they get closer to the atmosphere. This is the electron flux. This is from a design model. The new OneWeb satellites you might have heard of, which the British government's taken a $400 million stake in, they operate at 1,200 kilometers. if you look at this, this is the radiation exposure they'll be going through in this region at 1200. It's a factor of 10 higher than what you do at 800. Okay, factor of 10. So that's kind of interesting. Kind of see what may happen in the future there. All right, I'll move on to a different time. Okay. Okay. I'll just go over some of the other areas that space weather can affect. So GPS signals, 1.1, 1.6 gigahertz L-band. What we actually get is disruption to the ionosphere. I'm just showing here the ionosphere. The signals have got to go through the ionosphere, and the ionosphere creates a delay in the signal. But the ionosphere is not uniform, it's non-uniform. It has irregularities in it. And particularly during storm times, these irregularities grow through plasma instabilities, and they can actually cause significant group delay. Normally you're correct for that by using a model, but if you have lots of irregularities, that becomes very difficult. And you have scintillations where you lose the amplitude and the phase lock on your GPS signal, so you lose it. So this is really important in the equatorial regions. And the reason why it's important, of course, is, errors, gives you errors up to 100 meters. And so people have been looking at this, could you actually use these kind of GPS signals to land aircraft? So not great during a large storm. Satellite drag is another aspect of space weather, which is important. So these are two spacecraft, Grace spacecraft, two satellites, and Champ. And you can see the altitude. This one's around, it's around 400 kilometers. And of course, it's decaying, and then they boosted the orbit and decayed, boosted it, and then very rapidly came out. Higher up, the atmosphere is a lot thinner, but there's a gradual degradation, and then it starts to come down. Okay. So these things are going through the atmosphere, and then that's causing drag on the satellite, and eventually they'll re-enter. But when you have a magnetic storm, this is the interplanetary magnetic field, it's a measure of the magnetic storm. What happens, you can get large electrical currents which flow, as I explained to you, in the ionosphere, and they heat the atmosphere. What does the atmosphere do? It expands, it goes upwards. So these satellites which go through it now have extra drag on them, so they'll start to come down in altitude and they'll re-enter more quickly. In the first instance, what they do is they actually change the altitude of the orbit. So you can see here, a 100-meter drop an altitude at 370 kilometers. But the issue here is not just satellites themselves, you've got millions of pieces of space debris going on. So it increased the risk of satellites colliding with space debris, because all those bits of debris are moving too, and they're all going to be affected too. It's a major, major problem, which is a growing problem. Okay, so here's an example of tracking. 1989, there was a big storm. The US usually track all bits of space debris greater than 10 centimeters in size. They lost track of thousands of bits of space debris. It took days on their tracking system to go and reacquire them. There's about 135 million pieces of space debris that can disable a spacecraft right now, okay, floating around. And in 2020, there's 580 collision alerts. Can you imagine? Now you're a satellite operator and you want to move your spacecraft. You need to reduce those number of collision alerts. And to do that, you need more tracking, and you need to be aware of what space weather, heating the atmosphere, and the expansion of the atmosphere can do. Trying to predict that is really, really difficult. But trying to assess what the worst case is, really, that's very important. Okay, yeah, this has actually been an old plot now. This is just showing you the increase in space debris. Can't remember when it finishes now. It only goes up to 2012. But there was a satellite Chinese satellite anti-satellite test here. The anti-satellite test in the for the missile, the satellite, it was successful, and there's all the bits of debris that ended up coming. And then there was a collision between two spacecraft, which increased the amount of debris as well. And since then, there's been more things. We've had this defunct spacecraft with an old fuel system explode on orbit. And there's a whole series of those things just waiting to go, because they're dead satellites now. But one's gone, and you know that the rest of the series are probably going to do something similar. It's a really bad problem. So trying to remove space debris is really, really important, and trying to track it and avoid it in the meantime. Radiation storm. Okay, here's another one. Solar energetic particle events. This is the kind of a cartoon, if you like. Coronal mass ejection is throwing out these billions of tons of charged particles, but it's moving out, and it's pushing the solar magnetic field with it. Plasma, this is about plasma physics. It creates a shock wave. So this stuff moves faster than waves can move in a magnetized plasma, and they're known as Alfvén waves. After Alfvén, who predicted them back in 45, I think it was, got the Nobel Prize in 1970. And the shock wave is one of ways of accelerating charged particles very effectively in the plasma. And you end up with these high energy protons, which are accelerated at the shock, and they flow along the magnetic field in interplanetary space, and some of that may intersect the Earth. Here's an example. Yes, okay, you see, okay, zooming in. In a moment, you see the particles, and it's like very similar to the one I showed earlier. Particles go into the detector, there you go. That is, these particles are being accelerated at the shock and come into the detector and do that to the detector. Again, it's a single event abscess. Okay. These particles are so energetic, they penetrate the Earth's magnetic field in the polar region, and they can come all the way down. They can actually get down to the ground. This is a satellite, a polar orbiting satellite called POSE, and you can see where the red, where it's picking up and detecting these high energy charged particles in the polar region, both north and south pole. So it gives additional radiation exposure to those satellites in those regions, and also to the aircraft that might be flying underneath it. It also disrupts the communications, high frequencies. So what it does is it distorts the ionosphere, creates additional ionization. That additional ionization, if you've got a radio waves which are bouncing off the ionosphere, high frequencies, they get absorbed. And so you can't communicate with the aircraft anymore. They use this for even today with passenger jets at high latitudes. You still use HF. So come on another slide. Here's an example of one of those events. This is real data. Okay, this is the Bastille Day storm, yeah, 2000. Look at that rise time quickly. That's one day there. And all of a sudden, bang, the flux goes up by orders of magnitude, stays high, and then can take days to come back down. There may be one or three of these per solar cycle, 11-year solar cycle. In 1959, there's one of these events lasted 15 days. It couldn't communicate with HF radio signals for 15 days at high latitude. It lasted that long. I think it's a record. And these things, when they get down to the ground, they can get down to the ground, and they create isotopes, and they can be trapped in tree rings and ice cores. So one of the things that we do at British Antarctic Survey is we dig ice cores out, and we use that for climate studies. But actually, we now have somebody who's interested in looking at the radioisotopes to try and identify these kind of events back in history, which is really quite interesting. Because there's at least one publication I know of, and a few more, showing that the events back in history could be something like 10 times what we've ever seen in the modern era. So yeah, basically it can create beryllium-10, chlorine-13, 36 in ice cores, and there's an event they estimate back in 660 BC, an event 10 times bigger than we've ever recorded directly. So the biggest event we ever know of in recent times where we have direct measurements is 1956. And I think this thing was about 10 times bigger. It's really interesting research, and it's important because by going back and doing those old records, we can build up statistics on how often these things occur and how extreme they can be. And okay, this is just to highlight and emphasize the effects on aviation. So loss of radio communications at high frequency, 3 to 30 megahertz. Aircraft still use them when they have to go on high latitude routes. So for example, if you're going to go New York to, is it Beijing, Hong Kong, Chicago, Los Angeles, Delhi, those sorts of routes. And one of these events comes along, you can get the upsets in the avionics, you get a radiation dose to aircrew and passengers inside the aircraft. And these things will penetrate the aircraft. Radiation exposure to aircrew must be assessed by law. So the only dose limit for aircrew is set at 20 millisieverts per year. And if you have pregnant aircrew, the maximum dose during pregnancy is less than half a millisievert. Okay. And what airlines do is they try and re-roster aircrew to keep everybody below 6 millisievert dose. Put that in context. So assessment for 1956 event, if that would happen again, on one route, so London, Heathrow to Los Angeles, it's not even as high as this. It's calculated you get 7 millisieverts on that flight if you were on it. And a 1 in 100-year event, based on some of the records we have, including ice cores, estimate on one flight alone you could get 28 millisieverts if you didn't do anything. Of course, what you do, and there's the civil aviation authorities will do, would be to stop aircraft taking off if they knew that there's a big event in progress, or ask them to fly at low altitude, get more cover from the atmosphere, lower latitude, or land. And that's if you've got enough fuel to get. Imagine you're up here, you make sure you've got enough fuel, and it might take a little while to get to a safe place. So to put this in context, be careful not to be too alarmist about this. The natural background in the UK, you would get something like 2.2 millisieverts a year, okay, from natural radiation. And if you've got a dose of 20 millisieverts, that would increase your lifetime cancer risk by 1 in 1,000. So just, we need to be careful. We don't get too alarmist about this stuff. I thought I'd talk about the economic uncertainty. When you try and sort of like getting funding for research and you want to get money from government, justify programs, you have to go into some of this. And it's interesting getting some of the economists involved. So some original estimates for extreme event reckon it could cause $2 trillion worth of impact. I don't think anyone really believes that. And satellites are estimated at 30 billion cost of loss and replacement. When space weather was put on the National Risk Register and has been updated recently. More recent analysis now for the USA is showing that if you had a big power outage, you'd lose something like between $7 and $42 billion a day lost to the US economy. And that's basically worked out along the lines of what's your gross domestic product for the US per year? And if you didn't have electricity, you wouldn't be able to be productive. So that's effectively how they go about working it out. It's a reasonable way of doing things. Okay? And also taking into account supply chain. And that would vary according to the storm. For the UK, this analysis was done just recently for 100-year event, we reckon based on the current forecasting capability, the cost could be as high as about 3 billion. And if we invest in new spacecraft to give us warning and new methods of forecasting, we could reduce that loss down to something like 0.9 billion. So when you see that, then the government decided, okay, it's a lot more argument behind it, but it's worth investing some money into the space weather forecasting so as to reduce potential impact. So I'm just going to remind you, okay, timescales one, sun to Earth, 8 minutes for a solar flare radiation to go from sun to Earth, right? A radiation storm, as I was talking about the protons, the shock wave, which produces the protons, which is 8 minutes plus a few minutes. That's how long it takes, so very little warning. A coronal mass ejection that goes sun to Earth, quickest is about 14 hours, and it'll take 2 days. A bit more warning, it's on the way. And once that can trigger a magnetic storm at the Earth, that storm can last several days. So different timescales involved, and you can start to formulate different methods of trying to forecast and predict. How am I doing for this slide? I know it's probably a bit. All right, I'll go through a little bit, just to give you some idea of what we're trying to do in my team here at British Antarctic Survey. So go back to this, we're focusing on the satellites and the radiation belts. How do we forecast radiation levels in the radio field? And what we do is we've built up a computer model where we take data from a satellite here at the L1 position, and we use that to drive a model of the Earth's radiation levels. And the model is based on solving the Fokker-Planck equation, and it's a diffusion equation. Okay, I want to, I'll try and do this in videos. Is it going to run? I hope it's going to run. Yeah. So what you see here are the particles, these electrons bouncing to and fro along the field line. They're generating here radio waves, special kinds of radio waves, they're circularly polarized waves. And because the particles are spiraling and the radio waves are circularly polarized, the plasma wave, they can have a strong interaction with each other. And this is showing, in this case, it's showing the interaction where it dumps the particles into the atmosphere. So most of the time, these particles are trapped in like that. Here they're generating radio waves, and the radio waves, plasma waves interact back on the particles, scatter them, and they dump them into the atmosphere, and they're lost. That's the loss process. The same plasma waves can accelerate under other conditions, accelerate those particles and keep them trapped in the space, so they accelerate them. So the idea is here you have a circling, I'll just go through this fairly quickly. Okay. You have an electron which is spiraling around the magnetic field. Here's the magnetic field along here. We have a circularly polarized plasma wave. It's called porous crystal wave, porous wave. And because they're both, this is spiraling, this is circularly polarized. When we get resonance, in other words, the frequency of the wave, when the frequency of the wave, Doppler shifted by its motion along the field up to the cyclotron frequency of the particle. This is the gamma effect, and just a number. When this condition is satisfied, you get strong resonance, and therefore it means energy exchange between the lasers and particles. And you can energize the particles. Yeah. And this is the equation we solved. It's based on the Fokker-Planck equation. So I'll just go through and outline what it means. What we're saying here, the way in which the distribution of charged particles varies with time, that's what the left-hand side is saying, that's what we want to find out, depends upon a diffusion, so it's the diffusion coefficient, and how the particles vary with pitch angle, in other words, direction in which they're traveling, at constant energy and location. It also depends upon energy diffusion caused by those same waves, the diffusion coefficient, and how the distribution of particles varies with energy, but at a constant pitch angle in the case. And it also depends upon, this is radio diffusion term, how particles are transported across the magnetic field or diffused across the magnetic field, and how the distribution depends on spatial location. the constant. And we also have a loss term over here, which represents the losses to the atmosphere, and also losses to the outer boundary of the magnetic field, which is the magnetic field. So we solved this equation. It's a three-dimensional equation. And we spend most of our time worrying about these diffusion coefficients and how to calculate them. And I'm trying to understand how these measure these things, the F by the E, the F by the R, trying to measure them and put them into the model. So this is equivalent to a climate model, one of those huge models of climate, but we do it for space, the radiation belts. Okay. And we include various processes here outside the waveform reaction, but we've showed you radio transfer, losses to the atmosphere, losses to the outer boundary field. And this is the sort of thing. So particle distribution of particles are drifting all the way around the Earth. Remember I said because of the difference in the gradient magnetic field. You're looking down on the Earth in the North Pole here. This is the outer boundary of the Earth. So as this electron drifts all the way around the Earth, it encounters fluctuations in the Earth's magnetic field. This field is fluctuating. And they drive a diffusion towards and away from the planet, which we take into account. So we need to measure those fluctuations. They also encounter plasma waves, which I showed you in that video. So here is an example measured on a spacecraft. These are frequencies of a few kilohertz, highly nonlinear, and they interact through resonance with the particles and accelerate in some cases and decelerate them and cause loss to the atmosphere in other cases. And these waves sort of seen only around part of the orbit. So we have to take those into account. There's another class of waves over here, which has very different properties, which largely called losses to the atmosphere. And there's another class of waves, which we see over here, very effective at highest energies. Do the same thing, mostly they're called loss. And then we have motions of the outer boundary, which come and go, which we have to take into account, because if the outer boundary comes in, we can get huge losses as well. And then there are other transport processes and other waves, which I'm not showing here. I'm just trying to give you a flavour of what we do. These interactions take place on microseconds. We try and simulate this over a period of days. So we have to make approximations. Okay, so I'm just going to wrap up a little bit now. So we need to predict, okay, from the ejections, we need to predict radiation storms more reliably. We can do that by looking for precursors on the sun, large sunspot groups, active regions. We can make measurements in interplanetary space between the sun and the Earth to help us. But that only gives us 30 minutes reliable run. So really, the key issue is reliable. There are lots of false alarms. We're developing a model. This is actually operational now on the European Space Agency website. You can go there and within. It's called SARIF. And we'll do a forecast of the whole radiation belt. And we'll give you numbers which you can compare against satellite observations. Actually compare as a model against a satellite observation as well. And have solar wind interplanetary measurements to go with it to help interpret it. So that's where we are, sort of state of the art, and we're trying to improve that model, make it more. So summary, modern technology has become more vulnerable to space weather because of new technology. Power supplies, satellites, communications, navigation, aviation. We need more research to try and assess how bad things could be, a 100-year event. More modeling to improve forecasting and more data. And we need to assess the environment and the impact. That's it. Thanks for listening.
Right, thank you, Professor Horne, for the wonderful talk.
Yeah, it's a long time.
Now we have about 15 minutes for questions. So if anyone would like to ask a question, please raise your hand. And we can also try to take a few questions from our online audience. So please in the chat if you have any questions. And yeah, please.
So you talked a lot about the predicting aspect. What are the strategies to what you do when you know that it's coming. Just fly the lower, use the aerosol.
Yeah, okay, yeah, that's a really good question. So for aircraft, if you have a real warning, there are a number of things, and they have done this, so there are systems in place to do this. So you've got aircraft already up there, they're giving a warning, so you would descend, have more atmosphere above you, so you have more absorption above you. Or if you can reroute to go to lower latitudes, or if it's really bad, if the radiation levels become really high, you would ask them to land. So a friend of mine's was a captain on Virgin Atlantic, and he was involved in, he was actually involved in involved in space weather assessments, and he's now left Virgin Atlantic. But he was saying, you have a major disruption. Do you remember the 9/11 thing where they closed on American airspace? There's a major disruption to aircraft. You could envisage something like that actually happening, where you prevent aircraft from taking off, and everything that's in the air has got at least a high altitude, has got to find some alternative land. A major disruption that would cost for a couple of days. If it got that bad, it's possible it can get that bad. They had an event, I think it was 2005, where they did actually issue an aircraft. Actually, it wasn't that bad, but they did descend and take those kind of actions.
For satellites or land-based?
So satellites, the satellite operators, so it's kind of an interesting one. So it's the area I work mostly in. So the satellites, they decide they're going to carry on operating. They're not going to switch them off, okay? But the sort of things they can do and do are delay a software update. Okay, they're kind of like a little bit more subtle, a little bit more sort of second level. So how many times does your computer update, right? So that's true for a satellite, they do it quite often. So they delay that to a period when it's low risk. Something you're going to have more particles around and more chance your electronics goes wrong, they'll delay. Satellite maneuvers, they'll delay. They only want to do that when it's safe to do it. Same with launching spacecraft, they take space weather into account when they launch. They don't want to launch into a radiation storm and then do the maneuvers and things. Their philosophy is low risk. And you don't want to be issuing commands to do something because you might make it worse. That's their main concern. There's an example a couple of years ago, I've got it actually in publishing one of my papers right now, where there is a satellite, a geostationary, and you had an incoming spacecraft which was coming over to actually take its place. And they were going to move this one out, put in a graveyard orbit, and use a new one. And then they had a warning, even that was about a day and a half warning. Now it's very uncertain really about a day and a half. But they said there was a coronal mass ejection coming towards you. We don't know if that's all hell's gonna break loose or it's just gonna be something small until it gets there, because you need to measure the Earth's interplanetary field, and you can't do it until it reaches you. They took a decision that they did not want to do this maneuver if there was a chance that you're going to have high radiation levels. So they did the maneuver early. So they took the spacecraft out of geostation and then moved it off so the incoming one could take its place. And it's very difficult to stop an incoming spacecraft when you've done a maneuver. You've got to work out all the orbit dynamics to get it there and then to slow it down and get it in place. It's very difficult to stop that. So they took at least their one out early on the warning. In the end, nothing happened. They were safe. But they don't know if they hadn't done anything, would they have still been safe? And that's the difficulty with satellites, just showing that you really did save money. There's also a thing in the industry and in government actually. The solar cycle is 11 years. The mean time of a government is, what, how many years? 4 or 5, something like that. And it happens in companies too. People come, people go, people forget that kind of knowledge, and it's a bit of an issue. They don't realize how bad it can be. I showed the solar cycle thing earlier. So we're just starting on a new solar cycle now. And some projections are saying, well, it's not going to be as bad. Even the last one was pretty small. Others projections are saying, yeah, it's going to be high. We just don't know. It's very uncertain. So there are a couple of things that you can do for mitigation for satellites and aviation.
Right, with a question from our online audience, could space weather and satellites be contributing to climate change?
No, not really. There's not much evidence for that. Okay, so I'll give you one piece of work. Actually, one of the pieces of work we did, or one of the members of my team has done, what she was showing is if you have more CO2 in the atmosphere, as we are, now when CO2, carbon dioxide, goes up to the highest levels of the atmosphere, it acts to radiate energy away. And it's a net radiation, okay? So it acts as a coolant. And the upper layers of the atmosphere, because there's nothing else to reabsorb it, the upper layers of the atmosphere are therefore coming down and descending. So the satellites that are up there, they basically, and they use satellite drag to re-enter. They're supposed to be, there's an agreement that it's supposed to re-enter the spacecraft within 25 years. Their estimate is because of global warming, those satellites will be up there something like 30% longer, 8 years longer than they were designed to be. So that's one aspect of a relationship to climate change. But some people have talked about solar variability and its effect on climate change. It's peanuts. Yeah. Peanuts. Got to reduce carbon dioxide. Got to stop burning coal. Got to actually capture and take it out of the atmosphere.
Okay. Do we have more questions from the audience?
You mentioned these rare big events. Are they better correlated with the amplitude of solar cycle or its phase? Or is it a mixture of the two?
Yeah, that's interesting. There's still an ongoing debate about some of that. So some people say, okay, the extreme events can happen at any time. It's a random distribution, any time during the solar cycle. And the argument they've used for that is the 1859 storm, okay, which was a big storm. But all the analysis we've done since seems to suggest they're more likely to occur during the sort of either the peak of the sunspot cycle or the decline phase. So the analysis I did work with Sandra Chapman at Warwick, and she really led that study, and it's really good showing that, trying to go back through the records and showing that actually that was more risk during higher solar cycle records. So I think that's what my money would be on. It's more likely. You can't rule it out, but there's more likely to be a bigger event during peaks of the solar cycle. The standard is going for something like a 1 in 100-year event. That's what people try and use. That's what government uses for risk assessment. What would be the impact of a 1 in 100-year event? And this sort of thing like 1859 storm, which is about the biggest one, is what's used. Okay. You know?
Right. Do we have more questions?
The coronal mass ejections and how they interact with the magnetic field, if they cause like a flip of it?
Not. You mean a flip of the Earth's magnetic field? No, they're not strong enough to do that. The Earth's magnetic field is really generated in the core by the motion of currents flowing in the core, and there's evidence for that has changed, as you're probably well aware, over time, that has actually changed a number of times in history. But the magnetic field from the sun, the solar magnetic field, no, it can't do that. The closest in the magnetic field, or we have detection of the solar magnetic field, is pushing the outer boundary of the Earth's field in, comes inside geostationary orbit. We've certainly got observations of that. We think it's got down to about 5 Earth radii. Okay, and then the outer boundary of the field, strong enough, pushes it back out again. So it won't cause a flip, no.
All right. Do we have a final question from the audience? Okay, we'll get a last one from the Zoom call. What is the Earth's magnetic field significantly weaker over the South Atlantic area? Is this permanently fixed in position?
Is this
is this fixed in position?
It's changing very slowly. It's changing very slowly. We think it's due to just the motion of the currents in the core underneath. There's observations. It's moving, if I remember right, the Earth's field is getting very slowly weaker, and it's moving more towards South Africa. I'm trying to remember now. I think it's moving further east. But you can track it. People have tracked it. The European Space Agency track it. The motion of. They were quite interested in that. So since the year 2000, you can see that it's actually changed. And the reason is because low altitude satellites go through that region, and it's well known for causing upsets on the electronic components on the spacecraft. So, and some orbits are designed to avoid it. So some synchronous orbits are designed not to go through that region, to be sure. Otherwise, or else you've got to design for it, have a special protection systems and try and put in more shielding. It's difficult to do.
Right. Can we account for why that particular area is weaker and why it's moving?
I think it's just really due to changes in the core field currents underneath the mantle. And I think you need to go more to a geophysics person than me, a solid Earth geophysics person than me to understand that better.
All right, thank you everyone. That's all the time we have today. Also, thank you to our speaker again for the wonderful talk. So that will be all for tonight. Before everyone leaves, just another reminder that we are still taking membership sign up at the back. And if you have signed up for memberships recently, you can get your card as well right at the back. Also, the committee will be going for a talk later on. So if anyone else would like to join just for fun, you can come along as well. And other than that, that's all for tonight. And thank you very much, and see you guys next talk.